Is that one working?
I will give it about 1 minute more, see if we can get some more people in. And then we'll start at about 10:11.
There's some papers.
I think the session starts 10:15.
Oh, does it?
10.
Right now. Yeah, just right now. So people are going to start with. Whenever you're ready. All right. Hi and welcome to LCU14-201 binary analysis tools. I would just like to let you know that I named the presentation, but I did not prepare it, and I was informed by the guys giving the presentation that it's that's a bit of a misnomer. It's more of a talk on trace tools. So my name is Ryan Arnold. I'm the toolchain engineering manager for the Linaro toolchain working group. So this presentation will be a discussion given by Omair, Javaid, and Christophe, Lyon. You can find the presentation slide deck on Zarista, as well as the Eatherpad link, which I will be working on the Eatherpad over here. We'll be taking questions and taking notes during the presentation. This is for the benefit of the remote participants. That being said, we'll have time at the end for discussions and questions, but unless these guys feel otherwise, I think you can interrupt with questions during the presentation. Or would you prefer them at the end?
Oh, can be along the presentation.
Right. So if you have questions, feel free to interject, and then Max will give you a microphone. You can ask your question during the presentation. So for the in-room questions and comments, please use the microphone. This is not for you to hear, but it's for the people that are watching the live stream, and also for the benefit of our video archive. So now I'd like to turn the microphone over to Omair and Christophe. Thank you.
It's not in the screen.
One thing I forgot, if you are a remote participant, please use the chat window on the Eatherpad link. You can find the Eatherpad link on Zarista. There is about a 30 to 40 second delay between what the information that's given here and what you'll see in the video, so the chat window is the best way to participate remotely.
This is something.
Okay, so let me start. I'm not sure this is working. Can you hear me?
His mic's.
Is this working?
I did turn on.
Is this working?
Yeah. No, bring the room.
Those are not the room layers.
There we go.
Let you take
Okay,
start with that.
that's okay.
Yes.
Okay, so welcome everyone. Let's wait. Yes. So this presentation we talk about what we call binary tools, binary analysis tools, which in fact will be split in two parts. The first part I will show you debug helpers, which are known as the sanitizers. And after that, Omair will talk to you about debugger-oriented features, which are around GDB, which include reverse debugging, which is a recent feature, and also Perf monitoring and Prelink, which is an optimization for load time acceleration.
Hardware support. So we'll talk a bit about Perf, which normally kernel guys seem to use. frequently, but and the user space is not sort of user space people are not using it that frequently. And then we'll talk about Prelink as an optimization tool for speeding up your applications. So I'll hand over the mic to Christophe and we'll start with Sanitizers.
Thank you. Okay, so this is an educational presentation to present you the feature. It's not an in-depth presentation on how it works. It's more to make you know, to make you aware of their existence, so that you can use them to debug your applications. So what we call Sanitizer is a new feature which appeared a few years ago, I think, in LLVM, in the LLVM world, and has been brought much more recently in GCC, and there are several variants of them. So here we have a list of what is currently available. You have an address sanitizer, which is called ASAN, a leak sanitizer, which helps you identify memory leaks in your application. A thread sanitizer, which is here to help you debug data races problems. Memory sanitizer, which is another variant of address sanitizer, and in fact helps you identify uninitialized memory uses. And UBSAN, which is undefined behavior sanitizer, which helps you identify problems in your code when you are actually having construct which involve undefined behavior as per the C and C++ standards. So
just by show of hands, who in the room have ever used one of the sanitizers? Memory, thread. Okay, so about a third of the room.
Okay. So in the area of debug helpers, you may have heard of tools such as Valgrind. So this compares to Valgrind in the fact that you have to, it does instrument your code, and it has an execution time which is much shorter than using Valgrind, in fact. Because Valgrind will reinterpret your code, instrument in an internal representation and re-execute it, which makes it slower. The advantage of Valgrind being that you don't have to recompile your application. This sanitizer also rely on runtime libraries, which are shipped with GCC or LLVM for that matter. So the first one I will talk about is ASAN, which is a memory error detector. So it helps you identify errors in your application related to the use of addresses which have not been correctly allocated or which have been freed and used after the free, or double free errors, etc. So in general, the typical slowdown is about 2 times. How to use it? It's quite simple. You just have to add -f sanitize equals address as a compiler option. The generated code will contain calls to the runtime libraries, which will verify the pointer which are involved in all your code. There are special hooks to use it from under GDB, for instance. If you want to, there is an example just after that. In fact, when you execute your program without GDB, and there is an error which is detected by the ASAN sanitizer, the program is stopped immediately with a backtrace showing where the error appears. But if you want to debug inside, you have to use GDB, and you can put a breakpoint on this ASAN report error function so that you can catch it just before ASAN catches the control. You can also control its behavior more finely using an environment option which is called ASAN options, where you can control verbosity and things like that. So an example, I'm not sure it's readable. It's a bit a bit slow, a bit small. I'm sorry, but you have here you can see that you allocate an array in the stack, and then you not in the stack, in the heap, and you delete it and you return a value from inside that array. So the red line here is causing a crash, which is detected by ASAN. So here you can see what the compilation line here. I just added the -f sanitize equal address option, and then at runtime you can see that address sanitizer detected a heap use after free this address, and it gives you the PC. Then you have the size of the access and the backtrace. So normally it's quite easy to come back to the error. Next example is a leak sanitizer. So this is very similar. In fact, they are all very similar in usage. You just change your compiler option to fsanitize equals leak. So this is in fact a variant of the address sanitizer. So there is no additional slow line implied by using this one. As an example, here you allocate memory, and then you discard the pointer to the memory. When you execute the program, you get an error reported here. So it says memory leak with the size and the backtrace. Yes, sorry, Maxime.
So for the address and leak sanitizers, are there a class of memory problems that are not detected?
Well, I don't think so, in fact, but they are confined to the use of pointers, and they just check that the pointer you are using or forgetting to release are actually valid. You have a different sanitizer to check the actual use of the values which you are reading, which is called the yes. Yes, and sanitizer.
There is a class that's not detected.
Oh, there are plenty of classes not detected.
Yeah.
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 There are more things not fixed than fixed.
So one thing that's not detected, if you have an array, and not an array, if you have a structure with an array in it, and it's not the last element, you don't detect after that, accessing out to the side of the array, for an example. So that's one thing that's definitely not detected at all.
Okay. And do you know if there is work in progress to fix that, or you don't know?
I think there is. I can't remember. I think there's something in Clang also that already does that, but I don't remember the details on it.
So I know that Evgen is doing all this. He's trying to combine all the memory leak and address sanitizer into one big sanitizer.
Okay.
But so that will precede any new feature that is going to be added.
Right.
So once that is done, people then can start adding more features. But yeah, there's plenty of things that are not done.
Right.
Next one I want to present is the thread sanitizer. So it is used to detect data race conditions. You can compare it to the Hellgrind tool, which is part of the Valgrind family of tools. Here the slowdowns is typically between 5 and 15 times. The compilation flags you have to add to your compilation line is -f sanitize equals thread -f pi -pi. Here is an example, so hope it's understandable. In the middle here you have the code for the small thread example, which is writing something into a map here. And in this part you have the main program which has created the thread, and at the same time it is reading the same value in the map. So you have a data race because you don't know which one is going to occur first. Below here, the compilation line with the flags I explained earlier. And here you have the backtrace reported by the thread sanitizer, which warns you about the potential problem.
And how does that work on ARM? Pretty good.
Yeah.
So
The Android guys use it, I hear.
really,
Yeah.
because
TSAN does not work on ARM.
no, in fact, on ARM, to my knowledge, well, I will speak for GCC. We have the address sanitizer, but not the thread sanitizer.
Oh no, sorry.
Because the thread sanitizer requires a 64 bits
Yeah,
address
Yeah,
space.
thread sanitizer record, yeah,
Yeah.
64-bit.
It needs the extra
Yeah.
bits,
Yes, and
and it probably won't.
x86 is the only, x86 64 is the only port of thread sanitizer as of today.
Yeah.
Yeah. So regarding AR64, there is work in progress. I will talk a bit more about this later. You also have the memory sanitizer. So this is what we talked about a bit earlier. So this one is here to detect if the actual access is going to a valid memory address, which means it has valid input. So this one is much faster than Valfind. I have no example here because I am a GCC guy and it is not yet available on GCC, so I didn't try to use LLVM.
You should.
Then finally an example of the undefined behavior checker. So like previously, it's pretty easy to use. You just have to add a compilation flag, which is sanitize called undefined. And
Does UBSAN works on ARM on GCC?
on ARM, not yet.
AR64? It does.
It does? Really? It's
No, I mean, yeah, because I haven't built it yet. I haven't got around building this in Clang to test.
oh yeah, yeah, you're right.
Right.
It works.
It works. Good.
Okay.
Works on Next.
Nobody cares about Next.
Okay, so here I have given a few cases of the error which can be detected by this sanitizer. So for instance, you have left shift by a too large value, division by 0, division which cannot be represented in the target data type, yes. Reading of a null pointer value and signed integer overflows. So this can be quite useful to identify things which are not warned about by the compiler, but because it cannot do it at a compile time. So now a slide which I talk about availability. So this is a project which has been started by Google for LLVM, I would say 2 or 3 years ago, maybe a bit more. And the port to GCC is still ongoing work. It started in GCC 4.8 for x86 targets, and then you have to enable it target by target. So currently, yes, there is probably ARM, MIPS, Spark, I think. As we said earlier, the thread sanitizer needs 64-bit pointers, so we can make it available on ARM ARC32 targets. There is work in progress to make it available on AR64. So as a summary, is a table where you can see that we have the address sanitizer available on x86, AR32, and AR64. Well, I posted a patch a couple of weeks ago. It's not yet mainstream, but it should be soon. Oops. The link sanitizer is only available currently on x86 64 bits. Thread sanitizer, same thing. And the undefined behavior sanitizer is available on all platforms. The memory sanitizer, which is a great feature, is not yet available in GCC. I don't know if there is work in progress in this area. So
Which one?
the memory sanitizer, yeah, MSAN. I don't know, does it work well in LLVM?
Yeah.
Yeah, so...
Well, I'm not sure. I haven't tested the MSAN yet.
Yeah.
But maybe I did. I don't remember. That was beginning of this year, so
Okay.
I don't remember.
And yes.
Is this ASAN your patch earlier this year?
Yes.
Yeah.
Yeah.
And because you're waiting for it to be on the release or something.
Yes, in fact, so the story for those who are attending here too. In fact, since these features come from LLVM, when you want to do something in GCC, you have to, if you need to modify the sanitizer code, you have to push it in the LLVM side of the world to make it accepted there, and then it gets merged back into GCC. So for GCC developers, it's not straightforward. So yes, a few months ago, I did ask for some modifications to enable the support of R64 in LLVM side. So this was accepted, and then I just recently restarted to work on GCC. And in the meantime, some things had been changed in the libs on the LLVM side, so which made my GCC patch no longer work. So it took me a couple of
We need to make
weeks.
this process
Yeah.
better.
Yeah. So I managed to identify the problem, and now it's working. So I have a patch which is under discussion.
Could you talk through this slide for availability in LLVM for AH32 and 60?
You mean this one?
Like the next one.
The same thing, but LLVM.
I can't.
You can't?
No. I know that ASAN and MSAN and so the sanitizers should work all for x86, S64.
Very good. Yeah.
Right? And ARM support is waiting for members to get some interest and ask us to work on it. But so we build now this, and it builds MSAN, ASAN, and UBSAN, I believe. But it passes all the tests. It's the same thing as Romana said. It's green, but it doesn't mean that it actually works everything.
I guess the only thing I don't know about is LSAN. Is ASAN, UBSAN definitely work.
Yeah.
TSAN definitely does not work.
Yeah.
And then LSAN, I don't.
So it fails to build, so I just disable it.
So I have a question. Why would we need sanitizers if there was Valgrind? Or
Valgrind sucks.
what the necessity sanitizers were addressing that Valgrind was not?
I believe it's a matter of execution speed, because on large applications it can be a nightmare to use Valgrind because it slows it down so much.
And the performance figures that you quoted, 2 times for a memory for address sanitizer,
Yeah.
is that during execution, or is that the penalty for analyzing gathered results after the application has finished?
No, it's execution time. So the big selling point of the sanitizers over Valgrind is that you can compile with the sanitizer and put the code in production, and let it run. And then when things, because, you know, probably everybody got the same thing. It breaks in production. When you try to reduce the test, you can't. So if you have the sanitizers running in production, you have the log, and then you say, you know exactly what happened, right? So the address sanitizer is great for that because it's only 2 times slower. So you can maybe have like a staging area where you try to give the same heavy usage as the production, but the thread sanitizer, which will be the biggest thing, is 5 to 15 times, and then it's not good enough for production. It's like as bad as Valgrind. And you can't run the production system on Valgrind.
Yeah. Yeah, you can't run production system still not Valgrind. The other thing, the other benefit that the address sanitizer has, being inside the compiler rather than the Valgrind, is that it can actually optimize away some checks. Because you don't need the checks if you know it's in the address range, for an example. So it reduces the amount of checks that's done that you won't be able to benefit from Valgrind.
Could you tell us more about how they are implemented? Is there a runtime part, LibC, or how do they actually work? I work in the Android team, so we use a different libc binary and so on. So I was wondering how we can get this working in Android if it's interesting.
No, I think you are.
Right. Well, it's a separate library. So the Sanitizers, when he said he had a patch to make it work on AR64, is that those are the runtime libraries, and that the compiler includes calls to these functions to check addresses, check ranges, check everything. So this is why it's lower, because it has all these calls. It's like the mcount and all the other profiling tools. It's the same thing. And the Sanitizer is actually more the library that you have for the runtime that you just link together in your binary. And in the compiler side is just to know which functions to call, which parameters, and it just does it. This is why you say that it helps, because it's explicit what kind of check you do, and then you say, oh, I don't need to do this check, and then you remove stuff. So the library is not libc or any. So you can use with any C library that you want, and it's just include the Sanitizer library, and everything will be fine.
To make a note on the libraries, if you are compiling your application using cross-compilers, like the binary packages that Linaro provides, then if you compile it on your host machine and copy your application over to your target, chances are that your application will not run because there are no Sanitizer libraries, dynamic libraries installed. So make sure that whenever you use cross-compilers, together with Sanitizers, we also copy over any dynamic libraries that come with the compiler. So we do provide the libraries, they're all there. They're just on the x86 host machine, and you need to copy them to your target, like lib, ASAN, so, and all the others.
You can also compile it in as a static library. LLVM defaults actually to this being statically. It's only GCC that defaults it to being shared. For an example. What?
Yeah.
No, LLVM actually defaults it to being static. And that's by design. GCC decided
Because
the
LLVM
opposite.
likes to be statically compiled, and
Yeah.
it's just different.
Opposite is GCC, so.
Yeah. It's just good to be the opposite.
I had one question. In the TSAN example, you had PIE. Is that a necessity for TSAN? Position independent executables?
Here. Yes and no. Yes, because of the way Google does it. It's required because that's what they do. And it's required as of right now. I don't know if there's work to getting rid of Pi or not. I haven't looked exactly, but it's required as of right now.
Is there any warning if you don't?
I think so, but I don't know.
Yes.
Yes.
If you don't use it, it doesn't work.
Ah, excellent.
I tried.
Good. Good. Way in the back.
The last time I looked at ASAN, it has a whole bunch of sort of hard-coded constants that define the shape of the address space. Has any work been done to allow 64K pages on Arch64 as well?
I don't know for that particular detail, but I think it has been a bit improved in engineering-wise, but yes, I was a bit afraid of all these constants to be defined, and I'm not particularly happy with the
Yeah, so
definition of that.
So yeah, yeah, that is definitely a problem still, because I think even PowerPC was running into that problem, where the address sanitizer depends. Even Valgrind actually has a similar issue, at least for MIPS. I haven't looked for other targets where you actually have to compile in the page size. Now, the biggest constant is actually the one, not the page size issue. It's actually where the what's that called? Where the shadow memory location has to be at a specific constant. There is work going on to remove that, to be able to do that for the kernel, actually.
Yeah.
But other than that one, I don't know any other work that's going on to remove these special constants. The shadow memory is definitely big.
Yes.
Thanks. If my application uses non-standard memory allocation functions, can you teach, like the address and the leak sanitizer, that certain functions are to be considered an alloc or a free function?
That's a good question.
I don't think so. I think it's just override malloc and free functions. So if your allocator does not use them in the last resort, I don't think it's working.
There's some runtime that they added, but I don't know the exact details of the header that's there. But there is some function to do it. I'm trying to think. As if it underneath just calls mmap and mmap will be done correctly, and malloc and free underneath will be done, but not your custom upper layer one. Because the upper layer one, what it needs is actually a red zone to be able to do the address sanitizer stuff itself.
Okay, if there are more questions on sanitizers, we will return to them if we have time left in the session. Now we are continuing to the next part of the session.
Okay, so we are a bit short in time. I guess we have a lot to cover. I'll be talking about reverse debugging first. We've been investing a lot of time to support reverse debugging, GDB reverse debugging on ARM and ARC64. As of now, we have almost completed the instruction set that is supported on ARM, so there are not many instructions left that are supported as a record target. So I'll talk about a bit of record debugging and reverse debugging for starters, so that people who may not be using it or don't know about it as a GDB feature. So we have been sort of in last 2-3 years looking for a feature that allows GDB to execute instructions backwards, though it's not a simple thing to do. So what we came up with is to revert the state of an executable process in terms of memory and in terms of registers, so that we can have a stable sort of a view of our program if we step backwards. So what record replay is, record replay, first we sort of use the standard features that are already available, the core file features to record the execution state of a program. The execution state comprises of registers and memory routines, and then we save them in a core file, and then we can replay it from that part. The reverse debugging is somewhat an advanced form of record replay, where we can, while recording, we can step backwards and have sort of have the watch points and break points in reverse, and almost the same features, but obviously it's not. It has its sort of limitations. But it's the slides sort of have a lot more detail, so you can sort of download them if you like and have more detailed information from those. For forward debugging, you have ptrace and debug registers and debug instructions and hardware ability to sort of debugging in forward mode. Obviously, we don't have any reverse debugging capabilities in hardware. So what we do is then we sort of try to sort of figure out a minimum possible information that we require to record its state. And for GDB reverse, it's the memory and the registers, as I talked about earlier. So we sort of save the state, keep on saving it as we go on during the execution of the program. Once we hit a record, sort of we start the recording by issuing the record instruction, and then GDB execute instructions one by one and save them if they have any modifications of memory. So we save those memory locations, and if there are any modification in the registers, so we save those registers as well. And if we need to save that recording, we can sort of save them in a core file, and we want to debug on the fly, then we can debug as well. So GDB has sort of special commands for reverse debugging, that is reverse step, reverse continue, etc. And if we want to use the regular GDB stepping commands for backward or forward or backward debugging, then we can use that set execution state. If it is set to forward, then we can sort of do forward debugging, and if it's set to reverse, then we can move backwards with the simple stepping and other run control commands. For reverse debugging, the breakpoint and watch points features work as they do in the forward mode. So there is more in last few years, it's been integrated with the CDT user interface as well, and the configuration UI where you can choose and enable reverse debugging before you launching your application. And then there are run control backwards, as you can see in the picture that is showing the backward debugging buttons on the run control terminal. So you can step backwards from the Eclipse UI. That's an interesting feature if you have integrated GDB with the reverse enabled it with reverse debugging. So
question can they ask basically about how it works? Is it my understanding that you do single stepping actually for your program, or in order to record actually all the registers and under the GDB, or?
Okay, so what it does is that it simulates. It has a simulation target in the background GDB, and when sort of you issue a single step, it does a single step. But if you are doing a step over, it simulates that step over by doing single stepping in the background. So it's actually not sort of working the way in reality it should. But it's only a simulation of what it should look like. So in backward mode, it's more like a simulation.
No. I'm more concerned about recording information, actually, right? Once you record it, actually, kind of how you go back, it's more or less actually kind of you can imagine. But kind of how do you collect all this actual information when normal execution, and what's the impact of if you enable such collection? Actually, what's the impact on the execution itself?
Well, I'll be talking about the impact on the normal execution. Once you have gone back, then when you step forward, you'll be doing the simulation again, because it won't be the same.
Just let's say I run my process. I enable. Actually, should I enable this actual feature, kind of in order to collect that actual information? So I have information to go back.
The CDT will do it all by itself. When you enable the reverse debugging feature, it will all by itself issue a record on when you launch your...
Right, so GDB at that moment actually will start doing single step.
Yeah, exactly.
So kind of like how slow it compared to the normal execution? It should
a
be
lot,
like 100,000 times actually slower.
A lot slower.
Possibly.
A lot
So
slower.
that's what I was actually, and then my next question is natural, because yesterday actually we had a session about core side. Did you guys actually talking to kind of hook up actually, instead of just doing actually single step, just to enable actual core side actually kind of like program flow collection and retrieve it up to the extent that you can, whatever like buffers actually has for this user land. That would be, you have absolutely normal execution, but then you can kind of have actually this CDT and then actually your GDB logic about kind of going actually backward and forward in simulation actual mode. And that would be beautiful. Actually, frankly, there's a single step execution. I don't think actually it's anything actually reasonable actually would ever work actually. So.
Yes, exactly. With the hardware debuggers and the trace probes, you have the ability to do that. But if you are doing everything on software, there's nothing much you can do. All you can do is that you can improve the simulation, but at the end of the day, it will be a simulation.
Now, there's one thing that the Java does, which I'll probably be throwing stones at, but it's quite interesting, is in the Java debugger, they record, every time you enter a function, they record the state of the machine. So then when you're stepping through, you say, oh, I stepped too far, go back to the beginning of the function. So if instead of recording every step, you record every entry point, then going back is just a matter of going back to the state at the beginning of the function, and it's step down until you can even set a breakpoint and run, because that would be a lot faster than single stepping all the way.
Yeah, there is another software. It's by Firefox. It's also open for reverse debugging. They are doing the same thing, but the way implementation has been done in GDB, they are recording the state of every instruction at this point. So probably it requires a lot of improvement in that area, because it's taking a lot. But then if you keep in mind that your host machines are normally so strong that they can actually bear that burden for now. That was the understanding when they actually had this this implementation sort of accepted in first place, because they thought that because everything is being done on the host side, so probably you might not at this stage require a lot of sort of improvisation at that time.
So we had a similar performance benchmarking in this thing in the debugger in ARM, and at least we came to the conclusion that that was not acceptable. So I'm not sure why the GDB guys thought that that was acceptable to single step. So I think you guys should. Sorry.
It's a good discussion. It's a good discussion to have.
Yeah.
But discussion maybe It's a good discussion to have, but maybe this is not the right.
This is not the right
forum.
place. Yeah. I know.
Only because, this was the implementation, he was just extending it to work for ARM.
Yeah.
Okay, so there are a couple of use cases. The cyclic mode debugging, if you come forward and then you just hit a bug and you won't have a need to sort of restart your program again and again and reach that point. You can simply reverse from that point and then move forward. I'll be sort of, we are really short on time, so I'll be sort of running fast. But the other use case that I have is that for a particular record target, if you sort of experiencing a crash or a bug that doesn't come up so regularly, you can hit the record and sort of record the execution for that particular bug, and if it comes up, then you can just save the record and keep on debugging the problem using that record. So these are two main use cases that user mode applications have sort of, many people have sort of utilized these particular use cases, and as this is supported on ARM and ARC64 now, I think many people in that particular area might be using it in future. So we have a lot of limitations right now, and one is the log size, obviously, and then we cannot restore the state of the system. For example, there's a program that creates a file. Obviously, we cannot in reverse mode delete that file, or maybe if there's something being printed on the terminal that's not being restored, then in multi-threaded applications, the thread timings and scheduling information is all over the place at times. So it's more like debugging certain problems, but not all the problems, obviously, and needs a lot of improvement in that point. There is one project, Mozilla which has a lot, which claims to sort of have more efficient debugging features, and I've added the links to that. If somebody is interested, you can go in and have a look at it. So I'm really sorry that we are short on time, so I'll just go over the other thing that we wanted to talk about is Perf. Not many people in the user space are using it, so just for a motivation, we thought that we can just talk about it. I'm not an expert on it, but let's have gathered some information on Perf for you. So it's a superset of all the tracing software, at least on the Linux kernel, and comparable with the LTTNG system tab, etc. Allows lots of user space applications are available, and then allows lots of different performance related events to capture. So what it utilizes is that it has interface with the hardware performance unit, and it gathers information from that as the kernel and other trace points, etc. And so it has a big sort of event a list of events that it covers. It can answer lots of your questions, like the CPU usage, the memory usage, cache usage, and then some custom trace points as well. So there is a bit of information on what type of events it stores, and then this is a picture from one of the online blogs that I've got. It shows that how it covers the whole of Linux from top to bottom, along with other tools which are capable of doing it. But its the standpoint where it stands out is that it has a lot more good integration with its user space applications, as well as there are UIs available. Yeah, here's the UI. So there is an Eclipse UI for the Perf tools. You can sort of use these tools with this UI and have that information sort of the memory information of the call graphs and cache hits and misses and all those information will be one good catch that you need to be aware of is that you need to debug, compile your application with debugging information if you have to see the detailed some detailed source level graphs with this particular UI. So the links are there if you need to install. You can just follow these user guides as well. Perf has a sampling and analysis tool, and then there are other tools as well. The Perf record actually records the different events which you select, or maybe a default set of events if you don't select certain events. And then you can use Perf report and Perf annotate to sort of view those that information that is collected by the Perf record. You can view a list of events with the Perf list. I guess the command is Perf list, and you can also view the trace points which are available, which are made available by different kernel modules. So if there are sort of certain drivers that are providing trace information, those trace points are available in the trace list of trace events. So,
Omair?
Yeah.
We just have maybe 1 or 2 more minutes.
So,
minus 1 minute, you mean?
Minus 1 minute. Yeah.
Yeah. So we'll sort of squeeze this up, and I guess there's a lot of information on these slides. If someone is sort of interested in sort of digging this further, I have added the some of the links to the references. They can go and have a. There are some other tools as well which are worth mentioning, and these tools are also like, for example, LTTNG and System Tab. They are sort of scriptable and have, allows you to use certain languages to write your own trace events. So there are in-depth tools that you can use other than Perf. So the next thing is Prelink.
Let's skip
Omair.
Sorry.
Oh.
Yeah, we're gonna have to skip it.
Userland access to perf counters. Any thoughts of doing that?
Yes, please.
Yeah, I think there's more than just me that would like that and be able to actually have a library then that's built for that.
Yeah, so there exists a system call that you can issue.
No, no system call. Low overhead, no system call. I don't want system calls. You trap, takes a very overhead and everything. I don't want that.
So there were 2 mechanisms for getting user space perf events. So one of them is that you can do a select call, so that when an event triggers, there's the select rollback. The other one is that you share memory with the kernel, and the events as they happen, they get written into the shared memory region. So in terms of low overhead, the shared memory is the last overhead. But these mechanisms already existed.
Even though the ARM8 has a capability to enable read access to the perf panel in BL0. That's what I just want to read it. Cool. Setting it up, I can use the system. That's fine. I just want reads to be very quick.
I'm sure they're open to suggestions.
I guess when the kernel guys should be able to answer this.
Yeah.
I think it should be a collaboration between the kernel guys and the toolchain guys.
Yeah.
To come up with it.
Hello, myself Yogesh. I recently joined LNG group, and they have the requirement for the fast path, and we have benchmarked the performance counter access from the user space, and the same with the direct access from the user space with the ASM instruction, and I have implemented that for ARM V8 also. And if we have the requirement of just reading the performance counter from the user space, if we go through the normal perf subsystem, it takes much of the CPU cycles. And as Andrew mentioned, if you have only the requirement of the read of the performance counter, and if we create some library in the user space, that gives a nice reading. So I have created that as a POC. I hope on Thursday you might visit us and give me the feedback about the different direction and your suggestion. Thank you.
It's a good idea.
So why can't it just be verified with the MSAN
So the next session will be, the next toolchain session will be here in about 10 minutes. We can talk up until it starts.
Actually, doesn't it start
Minus
now?
7 minutes.
It actually starts in 3 minutes. Let me verify.
So the whole purpose of perf and no profile, which came before it, was that you want to save and restore the counters over context switches. You're saying, please can I have raw access, which is going to give me aggregated information from every context which is running. That's not what these things are supposed to be doing. And if you want to aggregate it, why don't you go and aggregate it?
All right.